Dynamic equilibrium. Let's look at this reaction. Hydrogen reacting with iodine to form hydrogen iodide. We've learned that the rate of a reaction depends on the reactant concentration. Usually a higher reactant concentration makes the rate go faster. So if we're starting out with just hydrogen and iodine, then the forward reaction is fast, right? Because the concentrations are as high as they're going to be. And what we saw in our kinetics experiment last week, what happens to the rate of the reaction as time goes on? It goes down. So as the reaction occurs, these concentrations drop, and the rate of the forward reaction decreases. But this is a reversible reaction. It can go both in the forward direction and in the reverse direction. Initially, there was no product, and so the reaction in the reverse doesn't happen at all because there wasn't any HI for the reverse reaction to happen. As the forward reaction proceeds, though, what happens to the concentration of the HI? It increases. And that causes the rate of the reverse reaction to increase. Okay? So as the reactants react, their concentrations decrease, and the rate of that forward reaction slows down. As product forms, the rate of the reverse reaction increases. So we got some pictures. I love pictures. So here's time zero. All we have here are reactants. The little white diatomic molecules, and what color is that? Is that light blue or gray?
It's supposed to be purple.
It's supposed to be purple? Okay. Lavender in the textbook. Okay. It always gets a little distorted. It's not even the same on my iPad and the computer screen and up there. Anyway, those guys. So we have no product. And here is a graph showing concentration on the y-axis and time on the x-axis. So initially we have a concentration of hydrogen and a concentration of iodine, and we have 0 HI. So here we have, I don't know why they didn't go with 15 seconds. Maybe they could have made the arrow shorter though. It just bothers me. It was at 16 seconds and 32 seconds? I don't know. Anyway, they go to 16 seconds. And now we've got some product that's formed. So I don't know where 16 seconds is on here. Anyway, it's one of those days. The hydrogen concentration is going down. The iodine concentration is going down. That means the rate of that forward reaction is slowing down. The HI concentration, though, is increasing. So the rate of the reverse reaction is speeding up and going faster. And as time goes on, here we're getting to these curves are going to flatten out. And we're going to get to this point where we're going to get the equilibrium established. And now, as time goes on, the concentrations of reactants and products are not changing. And the reason that is because the rate of the forward reaction is equal to the rate of the reverse reaction. It's not that the reaction stops or is finished, but because these concentrations remain constant, the rates of the forward and the reverse reaction remain constant. It's a little bit like a freeway, and you've got people going north and you've got people coming south at the same rate of speed, same number of cars per second. And if you were to take a picture at any given time, the number of cars at the north end and the number of cars at the south end would be constant. And yet it's not always the same cars. A little bit like a crowded airport in the middle of the day, assuming there's no blizzards or fog. Airplanes come in, airplanes leave. If you looked at the population, the number of people inside the airport over the course of, maybe monitored every half an hour, it would probably be relatively constant. Because you have people coming in and you have people leaving, but it's not the same people, right? It's not the same people in the airport all day long. Some of the people are the same, the ones that work there, but most of them are travelers coming in, travelers going out. So what we have here is the concentrations remain the same, But there is still a lot of activity going on. And that's why this is dynamic. There's activity. There's forward reaction and reverse reaction. Any questions? Really important to be able to think about what's going on. So, dynamic equilibrium for a chemical reaction is the condition in which the rate of the forward reaction equals the rate of the reverse reaction. Both of those forward and reverse reactions are still happening. The concentrations of reactants and products no longer change, but, this is important, they are not equal to one another. It's a common misconception. Oh, well, we get to equilibrium and we've got equal amounts of reactants and products. It's in the middle. No. There are reactions that are like that, but most of them are not. The relative concentrations of reactants and products, whether they're roughly equal or more reactants or more products, depends on the equilibrium constant. And that will be different for each chemical reaction, and it will also change with temperature. Yes?
Is it proportional to that, though?
It is related to the equilibrium constant, and we'll see exactly how in a minute. So any questions? So this is a picture that they brought back from an earlier chapter in the book, except now they got boring, and they're calling it Country A and Country B. But earlier, oops, that's the wrong thing. Earlier, it was Narnia and Middle Earth, which I thought was just so much more fun. So we're going to go with that. I don't know. You could pick either. You could switch them if you want. I just randomly chose the left one to be Narnia. So here we're thinking about these two countries, and initially this border is closed. You can't get from Narnia to Middle Earth. And as far as I know, that's true, right? You can get from Earth to Narnia by going through the closet, right? But how do you get from Narnia to Middle Earth? They're like from two different authors. They're two completely different fictional countries, right? They're not even in the same universe, most likely. Anyway, so here we have a whole bunch of people in Narnia, and we've got a few people in Middle Earth. And now we've opened the gate, and we're allowing immigration. Okay, so we'll pull politics in here too. So now we're opening the border to immigration. Narnia has gotten very crowded, and there's a lot of empty land in Middle Earth. So what are the people going to do? They're going to move, right? And so initially we're going to have a lot of people from Narnia moving to Middle Earth because they can get a farm over there and support themselves. There's opportunities, right? Well, that keeps going, and then what happens to Middle Earth? It starts to get crowded, right? And so then some people are thinking, well, yeah, I came over here because, there was so much more space, but now all these other people came over here, and I think I'm going to go back. And so now we start getting some people going back to Narnia. And after it reaches equilibrium, the rate of emigration from Narnia to Middle Earth and from Middle Earth to Narnia are going to be the same. Does that mean there's equal numbers of people in each country? No. If Narnia is a more pleasant place to live for whatever reason, maybe it's just geographically beautiful, or maybe the tax laws are better, or, who knows? Climate is nicer. Then there will be more people in Narnia than in Middle Earth, just because it's more desirable. But there will be equal amounts of people at equal rates moving back and forth, because people are always unsatisfied, aren't they? They're like, there's got to be something better. The grass is always greener on the other side of the fence until you go to the other side of the fence. You move, and then you realize, no, it was better in the first place, and then you move back. So anyway, that's the idea of that. Equilibrium, equal movement in both directions. Not equal numbers of people on both sides of the line. Okay? Any questions?